Hello everyone, I'm Zhenwei Niu, a PhD candidate in California University. It's a great honor to introduce our new work towards safe physical human-robot interaction by exploring the rapid stiffness switching feature of discrete variable stiffness actuation. Robots have been widely used in the manufacturing industry. We can use safety and efficiency as metrics to evaluate robots. Traditional industrial robots have high speed and accuracy, but they are dangerous for human users nearby. On the other hand, soft robots have the highest safety level. However, their working efficiency is limited. Currently, the collaborative robots are in between, but their performance still has limitation. Recently, robots with variable stiffness actuation have been studied to meet better trade-off between safety and efficiency. There are many VSAs based on antagonistic and independent motor setup. However, their structure is relatively complex, needs at least two motors embedded in the system. Secondly, they have a relatively long stiffness tuning time. There's another way to adjust the stiffness. Instead of continuous stiffness tuning, we can also change the stiffness discretely. Here we propose a discrete variable stiffness actuator. Instead of using another motor to control the stiffness, we change the stiffness by using the clutches to engage or disengage the springs that are connected between the input and the output. DVSA has simple stiffness tuning system, and more importantly, they can change the stiffness immediately to any levels, regardless of the stiffness gap. The detailed structure of DVSA is as following. There are mainly four parts: input, output, two planetary gear sets, and the stiffness tuning system. A motor with a gear head is connected to a ring gear, which is engaged with three spur gears. One small gear is directly connected to the spring, while the other two are attached to the clutches, and then connected to the springs. The other sides of the springs are attached to the spur gears, and the ring gear is coupled to the output shaft. How DVSA works to change the stiffness rapidly. One spring will be always connected. By using a combination of active or inactive springs, we can achieve full levels of stiffness. DVSA has simple stiffness tuning mechanism. The gear train and the clutches allow the system to facilitate fast switching amongst the stiffness levels. Besides, it has good scalability. These springs can be selected based on different applications. How to take the benefits of DVSA? One aspect we think of is that we can apply it to collision safety. Here we propose a pipeline for collision mitigation by taking the benefit of DVSA. We use a moment observer to detect the collision. Once the collision is detected, we immediately lower the stiffness and also change the tracking mode to gradical position to reduce the impact. We conduct 3 experiments to evaluate the proposed strategy. The first one is dynamic collision with obstacle. In this experiment, both joints rotate from 0 degree to 150 degrees. The obstacle is in the middle of the trajectory. The ineffective velocity is 1 meter per second. The force sensor is used to measure the impact force. First, the manipulator is tracking the trajectory. Once the collision is detected, all the clutches are disengaged immediately. That means the stiffness is changed from the highest to lowest level, and the tracking mode is changed to gradical position. We also did one control experiment without rapid stiffness switching. The results showed that with rapid stiffness switching, the impact force can be decreased by 50%. We also did one dynamic collision with a human user. In this experiment, the human arm obstructs in the middle of the trajectory, and the manipulator is placed with the arm with ineffective velocity of 1 meter per second. First, the manipulator is tracking the trajectory, and the collision with the second link is detected, or the clutch is disengaged immediately. That means the stiffness is changed from highest to lowest level. In the following 3 seconds, the manipulator can be easily pushed to anywhere. After that, the manipulator resumes tracking with the highest stiffness, and the collision with the first link is detected. Use the same reaction strategies, changing the stiffness and also change the mode to gradient compensation. Once the collision disappeared, the manipulator resumes tracking with the highest stiffness to the target position. This is a complete process. We also did one static near singular clamping collision experiment. In this experiment, the manipulator keeps slowly clamping the obstacle, and the force sensor is used to measure pressing force. We use the same reaction strategy to the collisions, change the stiffness and also change the mode to gradient compensation. We did 2 control experiments. One experiment reacts without rapid stiffness switching. The other one reacts without any reaction. The impact force results also proved the effectiveness of the proposed strategy for collision mitigation. Thank you for watching this presentation.